Today we will talk about momentum thickness. But before we can do that, we need to talk about boundary layers. A boundary layer is a layer of fluid in the immediate vicinity of a bounding surface where the effects of viscosity are significant, as can be seen in the image below. The boundary layers can be seen forming over the surface of the sphere as the fluid flows over its surface. But why study boundary layers? As engineers, we like to make things easy, and the boundary layer equations represent a simplification over the Navier-Stokes equations, which are extremely hard to solve in the boundary layer region. In the analysis of boundary layers, we determine three main definitions, namely the boundary layer thickness, the displacement thickness, and the momentum thickness. In this video, we will only focus on the latter. So what exactly is momentum thickness? Represented by theta, it is defined as the distance by which the boundary layer should be displaced to compensate for the reduction in momentum of the flowing fluid on account of boundary layer formation. This can be seen by the shaded gray area in the image. But why calculate it? Firstly, it's a measure of boundary layer thickness. Secondly, it's used to determine the drag on an object. And most importantly, it's easy. It can be easily calculated from the experimental data, and therefore, us engineers love using it. Now let us derive theta. Assuming inviscid fluid and incompressible flow, we can see that the difference in the momentum flux can be achieved by the fluid without and with the boundary layer can be achieved by the following equation. By definition, this equates to the momentum flux in a layer of uniform speed u and thickness theta, which can be seen in the equation below, where the left-hand side represents the momentum flux if it's replaced by a layer at a distance theta, and the right-hand side is the difference in the momentum flux without and with the boundary layer. This gives us the following equation. However, beyond delta, the free stream velocity is equal to the boundary layer velocity, and thus the equation for momentum thickness can be written as shows. As engineers, we like to simplify, so Blasius came up with a solution that easily helped us relate the momentum thickness to the position and the dimensionless Reynolds number, which is delta over x is equal to 0.665 over under root of Reynolds number. That's all on momentum thickness. Thank you.